So this is how the tree is going to work. So it's going to pick at random k data points from the training set. We'll be having a training set and a test set. We are trying to do a similar machine learning example. The decision tree will be built on the k data points, that is on the test data training data sets, and we'll be having an option to set or to define how many trees we want to grow in the forest. We can say 10 trees, 100 trees, or 500 trees. It is up to us. But always we should remember, when we try to use very large number of trees, we'll end up in something called overfitting. When you this overfitting, you will be able to understand well when we look at the prediction region. And I briefly tried to explain to you what an overfitting would mean. So that's what will happen if you use a very large number of trees in your forest, then you will end up in overfitting. So that should also be avoided. Okay, so you should arrive at some optimal level based on your you can fit in, like starting from 10 to 100 or 500 or whatever it is. You can experiment with the algorithm and decide for yourself which is the best fit. Okay, so once you have decided, once you are given the number of trees that you want to grow in the forest, then you can repeat these two steps. Okay, that is again training with the data based on the training the random forest on the training set, and build the decision tree associated to these data training set. Once you have done the first three steps, what you need to do, then you can make your prediction for any new data point. As we have understood, each of the tree as given by, suppose the n tree is the number of trees. If you are given 10, each of the 10 trees are going to predict a separate value of y, and the average of all the predictions is going to be taken, and you will get a final predicted value from the forest, not from the tree. Okay, the trees give individual predictions. The for a random forest algorithm will sum it up or average it up, and it's going to give its consolidated prediction. So that's how this is going. Decision tree regression. Okay, again the same data set, position, salaries. Let's try to execute, and just to recap again, like let's try to execute decision tree regression. By regression, we mean we are going to predict a continuous output. What we are trying to predict here is the salary. Let's see, let's get a feel of what the data set looks like in the first place. So position, level, salary. There are just 10 records here. Okay. And there are 10 levels and there are different salaries. But it looks like the salary is not very linearly increasing, but it is exponentially increasing. That's what we get a feel by having a first glance at the data. Level is in the second column, salary is in the third column. We split the data set, we picked up second column and third column and subsetted the data frame, and you stored it in a variable called data set. So now if you view the data set, you will not get 3 columns, but you will get only 2 columns. Hope you know why this is happening, because we subsetted, we just picked the second and third column, and we are interested in only those. That means we are only going to predict salary based on the level. Okay, so that is the problem on hand that we have got currently. Install the package. We use the package called rpart for decision tree. Okay, so random forest is going to be something different. We'll be seeing subsequently. So rpart, we install the package. I did it, so I don't have to install it again. I just need to load the library just in case it's not loaded, and I arrive at the regressor. The how to arrive at the regressor, this is the model. I'm building the model. Formula is equal to salary as a function of rest of all columns. Okay, rest of all columns. What are the columns available? Only the level. Okay, this effectively means salary as a function of level. That's all it means. And data is data set. Okay, we execute this. regressor. We had a problem here. Let's come back to this. Okay. So now we predict for level 6.5. So we know 1 to 10 levels are there. We have salaries, but we predicted for level 6.5. What was the figure that we got? 249.5K. Let's go to the data set. We predicted for level between 6 and 7, that is 6.5. And the prediction that the salary prediction that we got was 249.5K. Does it sound reasonable? I mean, when for level 6 it is 150 and level 7 it is 200K. Does a prediction of 249.5K for level 6.5, does it seem reasonable or not reasonable? Yeah, to me, it looks not reasonable. Okay. So probably our decision tree is not predicting well. Okay. So that is the essence that we need to know. Decision tree is not predicting well. So what did we do? So when we plotted the data set, plotted the model, we got something like this. We got a very straight regression line. We expect the regression line to be in steps. We know for decision tree regression, the regression line should be in steps or levels, but we expect a straight regression line. And we did fix it, right? How did we fix it? There are no splits here, right? There are no splits here. So we incorporated a parameter called split when we are trying to generate the model. This is what we did. rpart.control min split is equal to 1. This is the control parameter that we incorporated. Now we again try to predict. Now we get 250K exactly, but still this is a disappointing prediction. Okay. So when at least when we try to plot it, how does it look like? So we get a slope here, but we know for sure that the decision tree's prediction is not going to be a continuous between this range and this range. Between this range, between this range and this value of X, that is years of experience, it's going to continuously increase as per the regression line, but it's not going to be so. It needs to be in steps or stairs. So this needs to look vertical, not something like a logistic linear regression line. So what did we do? Again, we went back, we tried to adjust some parameters. Maybe I think what we did is we were trying to, this was not plotted in high resolution, so we increase the resolution now. So that's what we did. The resolution is 0.01. We increased the resolution and we got a far better plot. The plot looks okay, but the prediction levels are still worse. I mean, for 6.5, it's around still 250K exactly. And to me, it looks absurd. So now we get into our today's problem. So today's problem of random forest for regression as against a decision tree that we saw now. Okay. And we'll check how good it's going. So what do you think the prediction would need to be, or most appropriate figure for a level 6.5? Your views. The level 6 is 150K, level 7 is 200K. 6.5, what will be the more appropriate one? You know for sure 250K is no good. But 175, okay, that's one good figure. 175, 1.75 lakh. Okay, 175 again, same. Any other? You should also remember that it is exponentially increasing. I mean, this is not a linearly increasing. As you see, for 2, it is 50, 60, 80, 110. It just climbs up. It is exponential. That is also something you should be aware. I think most of you have given 1.75. So we know, like, at least what could have been a better prediction? That some idea on what could have been a better prediction that we have got now. We are expecting around 175, let us say. Okay. So now we do the random forest regression. And do you expect the prediction to be better, any better as compared to decision tree? Yes, right? Of course, because we are going to use a forest to predict it as against a single tree that we used earlier. So this is supposed to give a better prediction. So again, the same data set we are trying to import. When I view the data set, it is 3 columns. Again, the same exercise. We are just interested in the level and salary. That is the column number 2 and column number 3. Okay. So we subset the data set or the data frame and store it in the variable called data set. So we just picked up column number 2 and 3, that is level, and if you see the data set now, it will be only level and salary. So this is what we are interested in, just as we did for decision tree with regression. Now, what we do is we are going to generate. So what is the package that we need to install to use or create a random forest model? The package is random forest. You will definitely for sure not have the package already installed on your system. So you need to install it with this command, install.packages within quotes random forest. Just to be sure, random is all in small letters and forest starts with a capital F. Okay. And once you have installed, or if you have already installed, you can have this line commented, but you still need to load the package. Okay. That's how you load it. I load this package. It's loaded. Now I'm trying to generate the regressor line. Okay. The set seed is some random attribute that we are generating. If you use a different number, we'll try to get a marginally different result. Okay. But all of us to get the same result, we need to use the same number. So that way we all will be sure that we are going to get the same number. Suppose you try to execute the same example from the same data set, but you set a separate seed or a different seed, then you'll get a slightly different result. So that is the purpose, to just to retain uniformity in all the executions. We set a seed. Okay, and now we generate a tree. How does this random forest? The package name is random forest, and again the function. This is a function. This is also a random forest. Okay, this is the function to generate the random forest model. Okay, random forest x. If you want to know the details, click on F1 here. You will get a help. So data, the argument goes this way. Random forest within after the parenthesis x starts with an x, because the data portion is optional data frame, so we are not interested. Subset is also we are not interested. NA dot action, we are not currently trying to eliminate NAs. So straight away we come at this one, the X. What is X? X is a data frame first. It's a data frame. It's not a vector that we need to know, because when you pass vectors to X, it is good. This command is going to fail. This function is going to fail. you should pass a data frame, okay, or a matrix of predictors. Matrix of predictors means data frame, or matrix of predictors means all the predictor variables. Right now we have only one predictor variable level, so we are going to pass this. But if you got multiple predictor variables, you can pass those as well altogether. So right now in the dataset contains two columns, 1 and 2. I want to remain column number 2 and pass the column number 1 as the predictor. Okay, X stands for predictors. So dataset, remove column number 2, pass level 1. Now, when you see y is a response vector or a dependent variable vector. Okay, as as against X, which is taking a data frame, Y is taking a vector. Okay, so if it is taking a data frame, then I would have as well passed something similar to what I have done here. But this is a taking a vector, so that is why I had to come up with something like this. Okay, now this is a vector. Okay, and an additional command that we need to use is entry. We are specifying how many trees that we are going to use in our model. So this is going to use 10 trees. Now we execute this command. Good. Our regressor is ready. Now we can straight away start making predictions. Now, just as simple as that. So the how the syntax for the predict command: predict the model name. The model name is regressor in our case, and the data dot frame level is equal to 6.5. Okay, what does that mean? We are passing for the predict command as well. The object that we are trying to pass, the data set that we are trying to pass is we are taking it data dot frame, and the level is equal to 6.5. We are trying to pass similar to a data frame. We have got only one value in that 6.5 for which we want to make the prediction. So let's execute the predict command. It's done, and let's see how much is the prediction. Do you expect it to be better than what the decision tree predicted? The decision tree predicted 250K, remember? So let us see if it is going to be any better than that. 141,733, 141K or 142K. Is it good? All that I can say is it is different, but I don't know if it's good or bad. But I think it is a little bit bad because for level 6 it is 150K, level 7 it is 200K. We expected a prediction of 175K at least based on the polling that we did. But the decision tree that it predicted is 142K. So probably I'm not sure if this is right, but I'm going to take a chance by increasing the number of trees now. I'm going to say instead of 10 trees, I'm going to use 100 trees. Again, I generate the regressor, that is the random forest model. I've done it. I'm going to predict now, and let me execute y underscore thread. How much did it come? 166K. To me, this sounds a lot better and probably more realistic. 166K. Based on our polling, how much did we get? Around 175K. But this comes to around 166K. Probably this is okay. But let's see if we increase the trees to 500 trees as against 100. Will we be getting anything different? Let's see for ourselves. Okay, the regressor is ready. The random forest model is ready. I'm going to make the prediction for level 6.5. And Y-pred, where is my Y-pred? It's 161K. It's 161.3K. Okay. And I assume this is more accurate, but as compared to the previous predictions. But we may need to look at the model in terms of prediction regions. Is there any overfitting and things like that? Because why does a model try to overfit? Because it tries to accommodate all observations and classify them into the respective prediction regions as close to 100% as possible. That's what it'll try to do, and in that process, it will do overfitting. And overfitting is not good, okay? Because you will do the arrive at the prediction regions based on the training set, but when you test it out or use the actual values for prediction, then those values may tend to fall on the overfitted regions on the other side. So overfitting is not good. Let's see what overfitting means actually and how does it look in our prediction region. So again, going back, let's retain our number of trees to 10 and let's see what will be our visualization, how it looks like. Okay, this is it. I run this. Okay. So we are talking about the regress. So now the steps that we see here, as against our decision tree, the steps are more definitely more in number, but we do have these lines which resemble a linear regression. And for that, what we do, we increase the resolution to 0.01 and try to do it again. So this is better, right? This is better in terms of how it looks, but in terms of prediction for 6 to 6.5, it is around 250K. That's what we know. For 6.5, what was the prediction? It was, let me execute this prediction here, 167.4K. No, we did not. We executed the regression. Let's execute it again. Then we do the prediction. Ypred is 159.392 for 10 number of trees. And now what we do, now again I execute the regressor, try predict. So this is a lot different now. We are trying to, this is far low, that's what we got, and this is far low, and we were not happy with this prediction. So that is why we wanted to increase the number of trees. Okay, so the graph looks like this. To make it more vertical or steep, we increase the resolution. Now it looks better. From the visual point of view, the graph is okay. From the prediction point of view, we are not happy. So that's why we increase the number of trees to 100. Let us again see how the graph looks like. Oh, as against 10, you see the number of steps have increased. This is the previous graph. Okay, if there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 steps are there, And in our current graph, the latest graph, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 steps are there. So earlier we used 10 trees and now we are using 100 trees. So what does this mean? Do you think the more number of trees, the more number of steps? The answer is actually not. There is an increase in the number of steps of the stairs, but it's not going to be as proportional. We have increased the number of trees 10 times. Did we get a 10 time increase in the number of steps as compared to the model that we got with 10 trees? No, it is just 15. That is almost 50% increase. We did not get a 10 times increase. Okay. So it's going to even out at some point of time. It's going to converge at some point of time. And if it is 15 steps here, let's do it with regression with 500 trees. Okay. And what I need to do, I need to execute this set command again. Okay, this is the one with 500 trees. Did you see 5 times increase in the number of steps? No, almost the same. See, this is the previous one for 100 trees, and this is the one for 500 trees. So the steps have almost converged now. So you may get a better prediction, but in terms of number of splits, each step is corresponds to the split. In terms of number of splits, it's not going to matter much. Okay, so that is the essence of it. Uh, so, our what is the final verdict? Verdict is something that we are still not sure, but we only assume wipe rate of 163K is the best prediction. Okay, 163, right? That's what we got for one 500 trees. Okay, so this could be the best prediction, 163K. So this is a better prediction. Now, why we don't have a verdict yet? Because we can try to use another model, come up with another model for this instead of random forest and try to compare the results based on that. We could also do that. So let's hold on for now. And so that's about random forest for regression as compared to data decision tree for regression. How do we know how many number of trees? I'm going to say it's 1,000 trees now. And what is the effect it's going to make? It's almost the same. Okay, and your prediction? Did it increase? Or as against 163K, did it predict anything different now? Wipe rate is 164 marginally. Okay, so that's all. I mean, you know for sure now by having a forest of 500 trees more as against the original number of trees of 500, we still landed with the same figure, almost the same figures. Okay, so that means we are good to have it at 500 and do not want to increase it to 1,000. Random forests, now that we have fully understood how regression works and how a decision tree regression performance or prediction performance versus a random forest regression performance, so we have understood almost in to a great extent in entirety. Now we move to random forest classification. So we know what a classification problem is. Classification is you group them as a good or bad or something categorical or qualitative. So that is what is about classification as against regression where we have a continuous dependent variable. So again, we did a classification example yesterday. we can try to look at that, or just go ahead with this example, okay, and try to understand it more. So we are using a dataset called social network ads.csv. What it does, it is about social media advertisements. Based on the advertisements, the store chain or a group, the uh, such as Walmart or something, they are expecting the sales to go up. They are wanting to know which customer is going to buy the product that they've advertised in social network media. Okay, so that is the essence of the problem that we have on hand. So let's see the data set. So the data set contains user ID, gender, age, estimated salary, purchase. So what are we trying to, I think based on age, estimated salary, we are going to arrive at a decision whether the customer is going to purchase or not. If the customer is 19-year-old guy, and if his estimated salary is 19K per annum or per month, based on this, I want to predict whether he will be purchasing or not. These are actual figures. Now, in future, we'll be given a particular age and a salary, and I need to make a prediction based out of that, whether he's going to make a purchase or not. Okay, so how many entries are there? There are 400 entries. And as part of machine learning, we are going to split it into a training data set and a test data set. As usual, the training data set should contain more number of records. So we have a split ratio of 0.75. That is, a training data set will contain 300 records out of 400, and the test data set will contain 100 records out of 400. Okay, so that's what we are trying to do. Now we execute this command. So this is for splitting the data set. We have been doing this right from linear regression and logistic regression. So it is the same template that we are trying to use over and over again for ease of convenience as well as for ease of understanding as well. So we don't have to go around for multiple templates. Okay, now feature scaling. Feature scaling is something which you don't really need to do for a random forest classification problem. Okay, why? When you do feature scaling, when you are talking about Euclidean distances, means distances from the mean, distances from the median, how far each observation is away from the mean. If you are talking on those terms, then you need to scale it. Okay, for random forest, actually you don't need to scale. But having said that, we try to come up with the prediction regions based on a very high resolution graph that we are plotting. And if the graph needs to work, then it would be good if we scale. Okay, so just for the technical aspect of it, we are trying to scale it. Otherwise, random forest, you don't have to scale. In case you want to use this graph in this template, then you need to scale it. That is the only technical catch. So let's scale it. Let's again have we executed all the commands. Okay, let's start from the beginning. Okay, load the library, set the seed, split, training set, test set. Now we don't scale. Now we use the random forest What is the package that we need to load? It's random forest, again for classification as well, just as in regression. And it's a similar arguments as well. Here we have an X for the training set where we give the X, that is the predictor data frame. We just remove the third column from this. The third column is purchase. This is going to be the predictor or the Y part of that. So we removed it from feeding it as part of X. So that's what we have done. And the Y part, we have said this is a vector again, training set $purchase. So this is the vector. And how many trees that we are trying to use now? 500 trees. Okay. Maybe we'll start off with 10 and we can go or scale it up as we go by. So 10 trees we try to use. Random forest training purchase, the response has 5 fewer unique values. Are you sure you want to do regression? So now that we have done the classifier, we predict, the model is generated now with the training set. Okay, the classifier is the model, it is generated. Now while predicting, you can pass the test set data as a data frame. Now you can pass the test set. Okay, so this will be the predictions. Y pred will be the predictions. If in case I want to see the predictions, Y pred. Okay, these are the predictions. Data is getting carried over from previous executions. Let me remove the data set. Now again, I generate the classifier and I start doing the prediction now. Y underscore pred. So now again, what we do is something on this. We try to do this part, the purchase as a function of levels. So this we are going to factor the predictor variable or the dependent variable purchased, because it has values 0 and 1. We are going to factor it or set levels to it, saying 0 is one level and the next level is 1. So we do that, and now we try to execute the entire set of code. Feature scaling we opt to do. Now we did a feature scaling and we also did a factor. Now we get the predictions for the test set. The second observation will not buy, fourth observation will not buy, fifth observation will not buy, only the 19th and 20th will buy, followed by 32nd and so on. Okay, this is the prediction data set. Now let us do the confusion matrix to understand how many false positives and how many false negatives are there. So to display the confusion matrix, I again enter CN, and this is the prediction. This is the confusion. How many false negatives are there? Why? This is a prediction. This is the actual value. 0 has been predicted as 1. That means it is false positive, and 1 has been predicted as 0. This is false negative. So 6 plus 8, 14 predictions are RE or gone wrong. 56 plus 30 is 86. So out of 100, we have 86% accuracy of the model. So that's what it means. So you can, based on this, you can arrive at what needs to be given. You can use it for multiple purposes. We use it for confusion matrix as well. So once this thing is done, now we try to visualize. Run the code. It's going to take a while. Yes, it's done. And it's also going to take some while for the plot to pop up. Okay. We are not sure. Yeah, good. The plot has popped up now. So this is how so what is the green and red regions? As we saw from the very early examples from linear logistic as well, these are the prediction regions. Okay, these are the red is a prediction region where any observation that is marked in red, if it falls in the region red, those observations or those are the customers who are not predicted to buy the new product, and those in the green are predicted to buy the new product. Okay, how many trees did we use? We use 500 trees. Okay, maybe that's a reason. So what I call as overfitting is this stretch. Okay, this stretch. You see this here, red stretch there, and something here as well, and something here as well, the red one. Okay, so these are over cases of overfitting. Okay, what the model did is it desperately tried to accommodate all the red guys. Okay, so that's why it extended the prediction region, the red region, to those observations as well. But in the process, you also know that there are some green guys here. They have fallen onto the red region, which amounts to a wrong prediction. Okay, this is a case of overfitting where probably because you use a large number of trees, or maybe that is the reason, and that is why you got a overfitting curve, overfitting prediction regions. So the problems with overfitting is like when you use a test data, you'll end up with wrong predictions for the test data. The model will be accurate for the training data. That is okay. Based on that only it has arrived at the prediction regions. But when you use the test data, you will end up in when you run the confusion matrix, you will find a lot more false negatives and false positives. So always we should know that there is a trade-off between the number of trees or the model that we are using, and we should also ensure that it is not overfitted. Okay. So this is the prediction. Let's try to use something with 100 trees as against or 10 trees to give us a feel of how it looks like. Let me run the confusion matrix now. 6 and 6, 12. 12 are predicted wrongly. False negatives or false positives are 12 in number together altogether. And when we try to visualize this model with random forest model with the 10 trees, how does it look? Does it serve anything better in terms of overfitting? Let's discover for ourselves. So it's still executing, and it also takes time after execution for the plot to pop up. Okay, let's give it some more time. So meanwhile, so once you have done the, as we wait for the appropriate plot to pop up, so we can, yeah, this is the one. So this is even bad, okay? So this is even bad. You see the regions extending all into the green area. So the prediction regions are not very clearly demarcated, okay? And it tries to desperately accommodate the red dots in the green region. So it extended the red region. So this is what, and you find hazy red as well here region. So this is not good. Now, so you can just keep experimenting based on how many trees you want. Now you can go for 100 trees probably and try to do that. Okay. So this is all interpretation of how the prediction regions look like, and how your predictions are, and how your confusion matrix. When you say evaluating a model, confusion matrix is also a tool to evaluate the model, and also your regions that you are getting on the plot as well. So these are all tools to evaluate your model. Okay, good. So that's about random forest classification as well as random forest regression that we saw today.
I'm sure you enjoyed learning from this video. Please like the video, and if you have any doubts regarding this video, please comment us in the comment section, and don't forget to subscribe to our channel for more such informative videos. Do look out for other related videos in our playlist. For more information, visit our website now. Keep learning with Intellipaat.